Okay, give me just a few more moments while this is finishing loading up. We're ready.
Thank you, Dina. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society. We are delighted to have Dr. Dennis Bodewits this evening as our guest speaker. Dr. Dennis Bodewits is an Associate Professor of Physics at Auburn University. Born in Netherlands, he studied experimental physics and astronomy at the University of Groningen. He got his PhD after writing a dissertation on charge exchange emission from solar wind ions interacting with cometary atmospheres. Being awarded a NASA postdoctoral program fellowship, he moved to Washington, D.C. and started to observe comets and asteroids with the Swift Space Telescope at the Goddard Space Flight Center. Between 2010 and 2018, he was a member of the Small Body Group at University of Maryland, where he got involved in the comet flybys of the Deep Impact Stardust Next missions and in the Rosetta mission that orbited Comet 67P/Churyumov-Gerasimenko for over 2 years. Dr. Bodewits joined the physics department of Auburn University in 2018. He has authored over 130 papers on comets and asteroids, and International Astronomical Union honored him by assigning asteroid 10033 the formal name Bodewits in 2017. So, Dr. Dennis Bodewits, please proceed with your presentation.
Hey, so welcome everybody. I think you guys are very familiar now with the Zoom format. This is intended as an informal talk. I enjoy doing those, and I would love to keep you guys be on board while I'm talking. So if you have any questions, raise your hand or put in the chat. And I hope that Mehmet and all you can keep an eye on that, because if people are muted, they can't ask questions. But I'd hate to lose you at some point half the way. For me, it's Friday evening. This is informal. This is fun. So please interact and let me know what you're thinking. So I am a planetary scientist working on comets, and comets for me are very exciting because they are strange little objects that are the intersection between so many different scientific fields. Myself, as you will see, I am a atomic physicist, so I mostly work on the light that is re-emitted by the molecules in cometary atmospheres. But in order to understand that, I had to learn a lot. I had to learn geophysics, atomic physics, plasma physics, engineering even, and a lot of different things. So this talk, there's going to be a little bit of that, of all of those different fields. It's very interdisciplinary. So that also means that nobody is going to be an expert on all of those, and you probably will out-expert me in some of the fields that I talk about, and that's going to be fun. I look forward to your questions. So so I'm at Auburn University. You guys in Colorado, so a little bit farther west. Auburn University is a state university about an hour and a half south of Atlanta. So we're in the middle or on the eastern side of Alabama. It's a pretty big university, 35,000 students, very heavy on engineering. Tim Cook of Apple got his bachelor's degrees from Auburn. So we have some good some good people who got the degrees from here. So let's get started. All right, so Auburn is over here. This is Alabama, and this is where I was born, in the Netherlands. As you can tell, I don't quite have a Southern accent. I'm not from here. The Netherlands is a small country on the western edge of Europe. The weather is downright crap, even though your Denver weather is a little bit wild. I know that, but our weather is characterized by a lot of water. This actually is the prediction for this week, which is kind of nice. But on average, the Netherlands gets 100 minutes of rain every day. So this is not in downpours. This is just like distributed all over the day. And so whenever you met a Dutch person, talking about the weather is a safe bet. I was asking about like, hey, how was your commute? When were you biking home? Did you get wet? You got a conversation over there. 100 minutes of rain every day. And in fact, most of the Netherlands is famous for being under sea level. So this is a map of the Netherlands and the parts that are under sea level. It's most of the northwest of the Netherlands, and that's why the Netherlands have a lot of a lot of mills. It's not for milling grains; it's actually for pumping out water. So that was the potential energy that we used. As a Dutch citizen, I have to apply for my passport every time again. And this is the critical skill that you have to demonstrate, being able to bicycle in very stormy weather with an umbrella, in rain, and stay dry. And if you pass that, your Dutch passport is safe. So all of that is a sort of comical introduction into the fact that I've been studying water molecules in every possible form for the past 15 years. Water molecules are a funny little beast. We have a lot of water on Earth, and many of you know water is critical to life, right? A lot of the exoplanets that we study, we say like, well, if you contain water in a liquid form, you're going to have a planet in a habitable zone. And so just the presence of water, the distribution of water, and the origin of water are what I study in my fields. So here's another funny study. So there are a bunch of small stuff in the solar system. We call them small bodies of the solar system. And in a very simple scenario, you would distinguish between comets, which are icy rocks, asteroids, which are more rocky, meteoroids, which is the small stuff, meteors, which is stuff that burns off in our atmospheres, and meteorites that you found it on the ground. So in this case, you classify them based on the amount of volatiles that they occupy. So what is a comet? What is an asteroid? In reality, this is not that simple. And in fact, the International Astronomical Unit has no definitions of those objects. They just say like, you got planets, you got small bodies, and that's it. And that's a very wise decision. When I was an undergrad, my professor did not believe in this. So I did a project where I said like, hey, we're going to define comets, we're going to define asteroids, and I failed. And this is still Robbie. So I failed to come up with a clear definition of what is a comet, what is an asteroid. And my professor told me, it's like, you just didn't do your homework. I don't know. This is very simple. This is very clear cut. Everybody knows this. And I've spent the past 15 years of my career and probably the next 25 years of my career to rectify this conclusion. There is no clear-cut distinction between comets and asteroids and other small bodies. They're just leftovers from the formation of our solar system. Some of them have more ice, some of them have less ice, and that's the end of the story. So let me show you this this headline from the Auburn Opelika news journal. Auburn professor hopes to settle the score between asteroids and comets using NASA's new telescope. This would be the James Webb Telescope. And we've been approved observations of some comets that, or asteroids that would be hard to put a name on. Are they comets? Are they asteroids? We don't know. They are somewhere in between, and we're going to figure out what their chemistry is. So 15 years down, I still don't know what is a comet or what is an asteroid. So sometimes the picture is more clear. So what are comets? So we visited these 6 objects that are clearly active, they clearly have ice, and they are clearly part of the comet family. So the most famous one, I think all of you know that, is Halley, right? So this is an object. This is one of the lesser famous photos actually acquired by the Russian Vega 2 space probe in 1996. And Halley here is about 16 kilometers by 8 kilometers wide. It's the biggest object, the biggest comet that was ever visited by any spacecraft. It's huge. It was an incredibly difficult feat to pull off. There was a small armada of spacecrafts, 5 or 6 of them, that flew by Halley at different distances. The European most famous one was Giotto, but there was also Vega, and all of them had different instrumentation. And this thing was flying by at a really high speed. And also technologies to do this were not really developed. But what you see here is an object that seems to be consistent of 2 different parts with some intersection in between. And there were jets coming off. So this was a confirmation that in the middle of comets, and the word comet is ambiguous, it's the actually object that's seen on the sky, not specifically referring to the nucleus or anything surrounding it. It's an ambiguous word. So in this case, now it was found that comets had a nucleus that was a few miles or kilometers wide, and that was surrounded by a cloud of dust and gas. So years later, almost 30 years later, there was Borrelli, imaged by Deep Space Nine, which has a rather similar shape. Both you could imagine as a bowling pin, consisting of 2 major parts. Deep Space One was a technology-driven mission. It was the first ion engine mission to go to deep space. And then it was Stardust, which actually brought back particles of this comet, or rather of its dusty environment, bringing them back to Earth. There was Deep Impact, an American mission trying to figure out what the structure of these objects was, hitting a copper bullet into it. And then finally, 67P. So Mehmet asked me to talk about comet missions, and oh boy, this could be a lecture series by itself. So mostly I'm going to focus on what is the deepest comet mission of all of them. So about 67P, which was a European space mission that orbited this guy for 2 years. So comets. So comets are different from other objects in our planetary system in that they have elliptical orbits. And so in an elliptical orbit, you are, in about 5 years, you're going to go from very far away from the sun at a couple of AU, 3, 4 AU, to about 1 AU from the sun. And I think this makes them really interesting because this exposes them to really different situations. At this point, you're really cold, actually so cold that water can no longer sublimate. And you're moving this object to distances to the sun where the ices that are most prevalent in those objects will start to sublimate and disappear. And after 5 years, you do this again. So for a lot of comets, at least the most famous comets, and that's a population of about 50 or so objects, we have a lot of historical information. And I think that's quite unique. The cadence is just perfect for the human mind, right? They come back every 5 or 6 years, the most famous ones. And so technology changes in timescales of a decade. This is a little bit more delicate in the terms of when you think that comets like Halley, they come back every 80 years. Things don't propagate that quickly, but we have records going back centuries for some comets. So the archival record is really rich, but it only goes so far. Technology improves very quickly, and so spectroscopic observations, spacecraft observations, these things are typically limited to just 1 or 2 orbits. But comets allow you to study planetary science objects if they move across the solar system. And I think that's unique. You're not going to move Mars to different distances from the sun. You're not going to move the Earth, hopefully not, to different distances to the Earth. But comets allow you to study what happens if you do so. There's another reason why this is very important. So comets are leftover pieces of ice and dust from the formation of our solar system. They're the oldest organic and volatile material that we have and that actually are available for study. But there's a problem. They are not original. They have been heated. They have been processed for 4 billion years. And so in order to really understand what was the original composition of this material, we need to understand how comets age. What happens when you heat this stuff? How quickly do their processes change? How quickly do their organic molecules change? So comet science is a science of asking how quick do these things change, what is original about them, and what is not original about them. And that's, if you want to bother a comet scientist, that's the question that you can always ask them. It's like, hey, but how is this related to the original properties? So we'll see that question a couple of times come up. Okay, so here's that question illustrated. I think you know this. We start out with a big interstellar cloud that formed into a disk. This disk evolved into hotter and colder regions with more or less exposure to radiation. Planetesimal formed. Planets formed, the planets rearranged, and you end up with this clean solar system that we have now. So this is a more data-driven slide. So comets are all over the place, and there are lots of comets. There are about 400 known periodic comets, and at any given moment, there are probably something like 500 to 1,000 comets in the solar system. We don't study all of them. We only study the bright ones. That's a bias that solar system physicists have. But every now and then, comets get really close to Earth. And in the past, this probably happened even further. And this is how comets delivered both organics and volatiles to Earth. So just in the modern era, this is a list of how many comets were close to us. So I have it listed here. Lunar distance is about 250,000 miles. And astronomical distance is about 95 million miles. So just 2 years ago, there was a comet that got really close to Mars. This comet was named Siding Spring after the observatory in Australia that discovered it. And it got to within 80,000 miles from Mars. And that's about 25% of the distance to the moon. So that's creepy close. It doesn't happen often, but you can see that from a planetary defense perspective, this is very worrisome. Comets move at high speed, so if you have a comet that hits the Earth, that would be a great risk. Now this comet moving within 80,000 miles of Mars, NASA had this question like, oh, what does this mean to our assets? Is it still going to hit our satellites? Do we have to move around? So we did this study, and we didn't think it would be that much of a risk. And it turned out to be a really tiny comet of less than half a kilometer in diameter. And so the Mars Reconnaissance Orbiter, which is a Hubble-sized telescope orbiting Mars, was able to get images of this nucleus of this comet flying by. I would not like Earth to have an encounter like this. So what happened is that the exosphere, so the outer parts of the atmosphere of Mars, were heated a lot by the dust particles. And so this really contributed again to the loss of volatiles from Mars's atmosphere. And had it been on Earth, it would have been a really like one of the most intense meteor storms that you would have ever seen. So multiple reasons to study comets. Origins of organic material and volatiles, risk in terms of impacts, so different reasons. So I'm going to focus mostly now on one mission, and that is Rosetta, and what we learned on planet formation, delivery of organics, and how comets changed our solar system. So, as you know, we started out with a disk, and this disk has a distribution of gases and organics. At different places of this disk, you will have different processes. They're tiny particles that are projected from the heat from the sun, and you can get complicated chemistry there. In the most simple vision, you're going to have a temperature as a version of distance from the sun. And this is just a 1 over the distance to the sun square relation. If you're further away from the sun, things are going to be cooler. So what happens at these different distances? Well, if you want to have your different materials as a solid, you will have water ice at about 3 times the distance of Earth to the sun, and that distance is called 1 astronomical unit. That's the average distance of the Earth to the sun. And if you're even closer in that, temperatures are going to be hotter, and you need silicates and rocky materials. So that's what Mercury, for example, is made of. If you go further out, you can have more volatile materials, carbon dioxide, and that's known as dry ice, right? So you know that dry ice has a much higher sublimation temperature. You get it in the store as an ice, but it turns into gas as soon as you heat it up. Going even further out, you can see here there's carbon monoxide, which is a stable ice at temperatures as cold as 20 to 25 Kelvin. So as expected then, when you look at the different planets, and this is something you've seen before, the composition of your different planets will differ depending on where they were formed. So what is our thought now is that the comets were formed between Saturn and Uranus. So in this area here, 10 to 20 astronomical units away from the sun, where you can have solid CO, solid CO2, solid water ice. And then depending on where exactly this was, so from here to here, your comet is going to have more CO or more CO2 or more water ice. So what you want, what one major goal of comet science is at the moment is to determine what are they made of. Let's make a big inventory and see if we can map this then onto our current understanding of solar system formation. If we observe 100 comets, just to put out a big number, can we then say that they were formed here, 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 and here? And the whole story is going to be a little bit more subtle than that. We're not going to get into that, but there are other properties as well that we expect would trace back to the regions where comets were formed. So again, the big comet question, what properties are original and related to comet formation, and which properties were altered by their subsequent processing and heating? Now, what makes things a little messy is that about 4 billion years ago, we had a major hiccup in the solar system. So the giant planets, Uranus and Neptune, changed position because of the gravitational interplay between Jupiter, Uranus, and Neptune. And this resulted in the late heavy bombardment. And the late heavy bombardment is visible as the cratering record on the Moon, on Mars, on Jupiter, and the other airless bodies. So all the small bodies in the solar system, they were rearranged, flicked around the solar system, they hit the planets, and it was a mess. However, as a consequence, the small bodies now got organized in essentially 2 clean storage spaces: a Kuiper belt, which is around Pluto, so something about 75 to 100 astronomical units away from the sun, and the Oort cloud, which is about halfway the next star, and it's a spherical shell. And ever since, the comets essentially remained unprocessed. So as planetary scientists like to say it, they are fossils left over from the formation of the solar system. And that is where they differ from the asteroids. The asteroids, they stay between 3 and 5 AU, so between Mars and Jupiter, and they collide with each other, they're ground down, they become smaller and smaller. But the comets, because they are distributed in this large space, they just sit there untouched, unheated, until by galactical tides they are they're flocked again towards the sun, and they have a lifetime of tens to 50,000s of years until they are eroded down. So that's how comets are different from asteroids in a very broad sense. Now, this was first realized in the 50s by Jan Oort, a Dutch physicist working on galaxies. And somebody bothered him with the problem of comets. And so what he figured out is that if you invert the origin of comets, they all sort of came about the same place, so which was about 50-ish thousand kilometers away from the sun. Now, his paper would probably not have withstood current scrutiny. He looked at like 10, 15 comets and drew very broad conclusions. But this is the current family tree that we look at them. So if you look comets and you look at about how far away from the sun they originate, if that is over about 10,000 AU, they are likely dynamically new comets coming from the Oort clouds for the first time. And then these comets, it's a little bit more difficult to explain, but you look at their relation to Jupiter and how Jupiter affects their orbit, and that determines what exactly type they are. What is the important part here? Well, I think I have that in the next slide. Yeah. So let's have a look at this slide here. So this is 1 over the semi-major axis of a comet. And this is the number of comets in that bin. So this is a much more elaborate plot of what Oort saw. Remember, Jan Oort only had 10 comets to look at. Here now we have about 100 of them. And you see that the semi-major axis becomes the inverse of the semi-major axis becomes a very small number here. And the reason for that is that most comets are ejected out of the solar system after their first orbit. They interact with Jupiter and they're kicked out. And so the average jump, the average change of the semi-major axis of a comet is about 5 times 10 to the minus 4 inverse astronomical union. So this unit here. So what you see here is a distribution of how many interactions a comet has had with Jupiter. And so most comets only have had 1 interaction, and it was enough to be kicked out of the solar system. But there's a distribution, also a shoulder here, of comets that come back 4, 5, 6 times. And this is how comets evolve. Some of them get trapped into the solar system and they come back and back again, and eventually end up with something like Halley. So I'll give you a second to look at this now for this orbital evolution. This is a field that's completely new. It turns out that there are comets that we can prove that they come out of the outside of our solar system. At this moment, there's 2 of them. These comets, they came in at an angle that was almost 90 degrees of our ecliptic plane. So there was no way that they interacted with Jupiter, but still they have an extreme eccentricity. These comets are interstellar comets. They came from other planetary systems and they interacted with our sun. And this has changed our field in ways that I can just not describe. Can you imagine the impact of having a volatile object containing organics from another planetary system that passes by our sun, and we can and that allows us to study what their chemistry is made of? So there's the 2 objects. The first one was one Oumuamua, which was very rocky-like, more like an asteroid. But the second one, Borisov, that was definitely a comet like we know it. It had organics, it had water. So now we know that there are other planetary systems that have these icy rocky bodies with a lot of organics, and we interact with them. The astrobiological consequences of this are just massive. The reason why we are starting to discover them is that we now have robotic telescopes that are as sensitive as 20th magnitude that monitor the sky every night. But still, notice that Borisov was named after an amateur astronomer. You guys are still better at discovering comets than we are. And I think that's awesome. Okay, let me move on. So this slide is about planetary missions versus observations from Earth. Planetary missions give you a lot of depth. They are amazing, right? Seeing an object for the first time from a satellite, I can't tell you how exciting this is. You get a lot of detailed information, you fly a laboratory, but there's only so much you can do. Planetary missions are expensive. Planetary missions to comets take a long time, especially if you want to orbit them. That takes about 10 years. So the price you pay is that you can study one object in depth versus the dozens, if not hundreds of objects that you can study from the ground, even if you use large-scale objects. So what you can do from the ground is study larger samples. You can study events like outbursts, jets, breakups. You can develop shape models. You can see, using spectroscopy or other techniques, you can figure what comets are made of. You can observe them from one orbit to the next. So I marry both techniques, both ground-based or Earth-based observations with space missions, and I think they're invaluable. And so that theme will come back in the next slides that I show you when I talk about the results of the Rosetta mission. So this is a picture of the Rosetta mission. Rosetta was a mission from the European Space Agency with international collaborations. It was their flagship mission to visit a comet. It was very expensive. It was technologically very complicated. It was launched in 2004, and the mission ended in 2016, so 12 years of operations. It operated very far away from the sun, and I know that many of you are engineers. So 32 meters of solar panels, that's enormous. That's about 100 feet. And the reason why they're so big is that Rosetta needed to operate far away from the sun, about 4 times the distance Earth to sun, and study how the comet was active. So with the total length here being 32 diameters, this central hub is about the size of the room that you sit in, probably. And also this antenna is enormous. And we were still fighting over data transfer. Who gets to which instrument gets to transfer the data today, and how much pictures can you take? So if you worked on spacecraft or any engineering, then you know we love our acronyms, right? So here's a bunch of acronyms. But what Rosetta carried was a wealth of instruments and cameras. There were optical cameras, there were infrared cameras, there were radio instruments, there were mass spectrometers, there were infrared spectrometers, and so on and so forth. So this was a flagship mission, and it had instruments that could sample the environments as measured in place, and also instruments that could monitor the comet from afar. It was very rich. So let me move this out of the way. It was a very long mission. So the difficulty of getting to orbit a comet is that you have to catch it in its orbit. You have to move around, and then approach it really, really slowly. And that's going to take you years. So 12 years typically. That means 2 times around the sun for the comets. And Rosetta was a first in that it both had an orbiter and a lander on board. And this would also allow it, differently from missions before, to study the comet both far away from the sun and much closer to the sun. And I think that's that was a lot of the key science results that came back from the mission. So this is a timeline. It did a lot of things, and this is very typical for any of those missions. You're going to do gravity assist, some observers on Earth, actually forgot that Rosetta was a man-made mission, and they classified it as a possibly hazardous asteroid hitting the Earth. I think that's one of the best parts of the story. But what just astounds me most is this episode here. Look at it. 8 June 2011, enter deep space hibernation. 20 January 2014, exit deep space hibernation. So for 3 years, Rosetta was switched off. Now think about this. Take your favorite laptop, switch it off for 3 years, put it in a drawer, and then, I don't know, a day before the most important interview in your life, let's say you got a job interview there, you're going to take that laptop out of your drawer and you boot it up, expecting that it works just fine. Are you nervous yet? There are not a lot of engineering companies that like this approach. And it had to be done because Rosetta went so far away from the sun that they didn't have enough energy to operate their mission. But boy, this is not my choice of doing things. But it worked, and it was a great celebration. Rosetta switched back on, all the instrument tested, they worked, and for the next 2 years, every instrument on Rosetta worked. There were some mechanical failures, shutters that stopped living, but that was as expected. So, this is the Earth flyby. Get a picture of it down there. Steins, Lutetia, different asteroids that they flew by. So, what did we learn? So, the business of going to a small body in the solar system is actually quite funny. And I know this as a mission scientist who writes mission proposals. So there's this thing that you want to do. You have your science goals. This is what I want to figure out. You figure out, okay, this comet is perfectly placed. If I'm launched in this year, I'm going to get there. It will work with my propulsion. I have the power on my system. And then ESA or NASA tells you, it's like, hey, your launch is actually delayed by 2 years. Figure it out. And your whole story disappears. So for Rosetta, they initially actually planned to go to a comet called 46P Wortonen. They were delayed by 2 years. They had to pick a new target, and 67P happened to be the only target they could get to. Not much was known about that object at that point. We knew its orbit, and that was enough. And that's how this works. This is the comet you can get to for the budget and the launch parameters that you have. So work with it. So people, as soon as you pick a target, people around the world are going to study this object. And so Philippe Lamy, a French scientist, used the Hubble telescope to figure out that this object had a rotation period of about 12 hours. And people reconstructed the shape, saying like, oh, this is what it looks like. I'm not really sure how to describe this. Maybe a diamond in the rough. So this is all that the engineers had to go by. And then you have your spacecrafts gradually getting closer to this object. And those were the images that they acquired. I know that they're a little bit hard to read in 2 dimensions. They're a projection. But this is what we tried. So first we said, like, this sort of looks like an apple core. Right? You see that over here. But then new images came about. And people said, like, no, this is a rubber ducky. And that's the image analogy that stuck. So every Rosetta scientist, every scientist working on this has a rubber ducky to look like, what does this object look in projections? And yeah, so there really is a larger lower part and a smaller upper part here. It's a pretty good analogy. So to phrase that in somewhat more, I'll get there in a second, scientific terms, this is actually wonderful targets. So remember again the prime directive in comet science that I told you before. Is this evolutionary, or are these original properties? So if you look at this object, and so for example, look at it over here, you would really say like these are 2 snowballs that were stuck together, a smaller one and a larger one. If you look at it this way or this way, it doesn't quite look like that, right? So is this now maybe an object in which some parts of the comet were eroded away? So I think that's a really good illustration of the question. Was it formed this way? Was it eroded this way? And so I'm going to show you a video that was made by a person who's actually not associated with the Comet mission at all, but it's just a science enthusiastic. And he put together some of the images acquired by Rosetta's cameras in a fantastic way. And it shows you how this is a geological object, how the environment of this object is really challenging with dust particles and meter-sized objects flying around, and just overall how wild the surface of this object is. So bear with me. So let's see if we can get this to play. So these are the solar panels of the Rosetta spacecraft, and this is the object rotating underneath it. So what I want you to notice there is the contrast between very smooth. I'm not a geologist. I'm an atomic physicist. So, but what you will see is very smooth surfaces versus very rocky surfaces. And you guys are in the Rocky Mountain area, so you're probably a much better geologist than I am. But the smooth areas are actually fallback materials. So what you get is snow from one end of the comet falling back onto the other end. And so questions that we have is like, how deep is the snow layer? How long does it live? Which are the older parts of the comet? Which are the newer ones? And all of the Rosetta mission was about how complicated cometary surfaces really are. And this is such a weird geology, such a weird surface. It's nothing that we know of. You got this really low gravity area. The gravity is 10 times, 100 times lower than it is on Earth, but it still plays a role. So let me play the video a little bit more and enjoy what you see. So yeah, here you see a lot what seems to be there are two things. So you seem to see what seems to be static noise, but that's not noise. That's actually dust particles and grains flying around the comet. So snow being lifted. And this really freaked out the spacecraft. And it made the spacecraft back away from the comet. And we didn't dare to go back as close as we did previously. What you also saw is that there was little lander drops on the surface. And we're going to see more of that in a second, or at least in my presentation as well. I don't want to run the full video. It's awesome. It just takes too much time. But so from an engineering point of view, so we went to this comet, and remember again, this was launched long ago, and the navigation cameras were based on finding some stars, processing with an algorithm, and determining where you are. And so now it turns out there were so many moving objects around this comet that the navigation cameras really freaked out. So from an engineering point of view, it was fascinating. This is a relatively cheap component of the spacecraft, but it turned out to be its Achilles heel, and really resulting in the spacecraft having to go a factor of 10 further away from the comet than they wanted to be. But the cameras were old enough that nobody knew how to reprogram it. It's a relatively, for me as a scientist, a relatively easy problem to solve. But now it's part of how you're flying your spacecraft and risk mitigation. So you're not going to touch this, right? This is something that could have serious consequences. So it's a $100,000 component of $1 billion spacecraft that makes you want to be really careful. There's an engineering class in that. Let me get back to the science. So this is a wonderful image that was also made. So this is the size of 67P. If it were to be superimposed on Los Angeles, in reality, the object is so weak that it would just crumble and fall apart. But it's a small sized object. They're not big. Okay, so let's get back to the science a bit. There are three aspects here that I'm going to illuminate. So why this was relevant, and that's how they are formed, how they may be or may not be related to water on Earth, and how they may or may not be related to life on Earth. So the first, and this is a purely geological object, and I love this. This is not my field, but I love the way that scientists in this field argue. So if you treat this object consisting of two lobes as a pincushion, and you look very carefully at different layers of it, how are they oriented? Then geologists argue that those are two independent objects that would look like two independent pincushions. So looking at the layers, they argue that Comet 67P was formed from two objects that very gently got together, as opposed to one object that was eroded. So getting back to that major question again. And that's fundamental to comets. This is why they are different as asteroids. Asteroids, we know, started off as 200 to 300 kilometer sized objects that collided together and were ground down to smaller bits and pieces. This is not the way for comets. Comets are pristine. They may have merged, but they are not the product of collisions. So that helps, because it means that they are truly the fossils of solar system formation. They are processed, they are heated, they are altered, but there's still this pristine nature of them. Next up, how quickly do they evolve? So this is always easy to tell in Alabama. So comets have seasons, and their seasons are not symmetric. And what that means is that you have a very long but cold northern summer, where the north is exposed to the sun and the south is not. But once they get closer to the sun, you have a short but very intense southern summer. So what that means is that 75% of your mass loss of your evolution is happening in that southern summer. It's really intense. And as a consequence, you really have two objects in one. You have this gradual evolution of the north, and you have the really rapid evolution of the south. And so when you see those images from left to right, you can tell that, right? So you see that the southern hemisphere, it has rough patches, exposed geology, whereas the north is capturing dust that is, or dust particles that eroded from the south. They fall back on the north because it's really cold there. So this is really smooth with a lot of fine dust being deposited. And this is really rough. You can see the terrain there. So the thought is now that any properties of the comet in the south are older, more inherent to the original properties of the comet, whereas anything that you see in the north is more process properties. And I hope that makes sense to you. It's a little bit difficult to get your head around, but it makes sense. So here the erosion, the propagation of heat are at the same rates. And here this is slower. So then there's this. This is a long-standing debate. Did comets deliver water to Earth? It's straightforward to say that the answer is yes, because comets contain a lot of water. But it turns out if you look at the relation between water and heavy water, comets actually have more heavy water than Earth does. And what we've now found is that there is a range of water, heavy water in comets, but it seems to me that the asteroids are winning, and specifically with things that we know now, that an asteroid-like Ceres actually has a lot of water, much more so than we expected, that it's likely the collision between asteroids and Earth that delivered water to Earth. But the numbers as of now are so small that every next comet observation can change the picture. And that's exactly what happened. There was the observations of Comet Hartley 2 with the Herschel satellite that said like, oh, the D to H ratio, the deuterium, the hydrogen ratio of comets is exactly as Earth. So comets must have delivered water to Earth. And then when observations of 67P came in over here, the story was reverted saying like, no, comets did not deliver water to Earth. So these are very hard observations to make. But the impact is enormous. So this is sort of an open question. Other chemical hints. It turns out the comets had a lot of molecular nitrogen and oxygen, and those are staples in Earth's atmosphere. So what's the big deal, right? Well, they're very reactive, specifically oxygen, right? You know that because oxygen causes flames. Oxygen is one of the most reactive molecules, and it also sublimates at really low temperatures. So there's no way that you would expect to find a lot in an icy body, but yet there was. And this is a big challenge to current models of the chemistry of protoplanetary disks. It hasn't been resolved just yet. Maybe part of the story is in how this is stored and released in comets, but we'll figure this out. And then this one, this was a press release from the European Space Agency. They made it look really cute, but what they wanted to say is that there are over 50 complex molecules in cometary atmospheres. We don't quite know how do they get there. Are they stored in the comet nucleus in the ice? Are they formed in some of the chemistry in the gas phase? But most importantly, there's glycine, so amino acids. And they got all sort of fun stuff. There's sulfur chemistry, cyanogen. Here's so the argon, krypton, and xenon, which are really interesting because they are not reactive at all with any other species. They're noble gases. So the chemistry in cometary clouds or in the clouds surrounding comets is complicated, rich, and surprisingly organic. And that is something that we're hoping to understand going forward. So what are the next steps that we can do? So Rosetta orbited this comet for 2 years. It had a wealth of instruments, but there are things it could do and it could not do. So it could not look below the surface. So all that we know is gases surrounding it, but not what is stored in the comet. So what we really would love to do is bring back a sample of a comet to Earth and feed it to all the laboratories that we have and really, really look into the chemistry. That's going to be expensive. It's going to take a while, but I think it's worth the effort. I'm going to get back to this. Let me move forward for a second. Oh dear, I have a lot. For this, there currently are 3 or 4 NASA proposals to go to a comet and bring back a chemical sample and analyze in our labs. And as you all know, there is so much more that you can do in the lab that you could ever do in a spacecraft, right? So that's why this is the next step. Europe has a similar plan. What Europe tries to do at the moment is actually to fly to a comet that has never been passing the sun before. So get a really, really old fossil and look how that looks like. There's no way you can orbit those kind of objects. They come in at a really high speed. They move at really difficult orbits. So you only get one shot at imaging it. Which orbited Churyumov consisted of 2 parts. It had an orbiter with the instruments that I explained to you before, but also a little lander on board. It's table sized, probably about the same size or half the size of your typical coffee table. European Space Agency tried to land this on the surface, and as they like to say, they not only landed it, they landed it 3 times. Other people would say that, like, yes, it landed, but then it bounced a couple of times before it finally found its resting place. You guys are engineers, so I can say this. It was over-designed, and a lot of things didn't work. It had a harpoon, it had a thruster on the back, and none of this worked. There were problems with the explosives that they used. So this poor little thing called Philae, it bounced on the surface. There you go. This is what it was launched from the spacecraft. And it was orbiting, it was going down. You got some dark spots that are solar panels. It has 3 legs. So it's going down to the surface. And it bounced 3 different times before it got to its spot. It was over-engineered. It had a lot of instruments on board. And the most important one, I think, or one of the most important ones, was a radio experiment that would allow Rosetta to transfer a radio signal through the comet and find out what its interior would look like. And for that, you really had to know where it was on the surface, but we didn't know that. And so the mission searched and searched. And the French military was employed. Apparently, they were really good at finding objects on surfaces. And they had 3 or 4 sites where they thought that the object could be. And we tried to aim Rosetta, the orbiting spacecrafts, at those sites to find it. And that's actually really hard because this spacecraft was not just orbiting it. The gravity of Comet is really small. So you have an irregular orbit around it, and you only know the pointing of the spacecraft after you fire the thrusters. And then over time, the uncertainty of where you're pointing at the surface is building up. And so eventually they were lucky enough to find an image of the little lander. And you see that it's right at the edge here. This was found by a graduate student who had a lot of time, and he must have gone almost insane looking at those images. So what they found was this little leg sticking up at the edge of this image here in the shadow of this rock. And this is how the lander was found, almost when everybody giving up and ever finding it. Yeah, that's the end that I have. I hope I gave you an idea about cometary science in general, how they are challenging to send space probes to it, even if you have a lot of patience, demonstrating that you need a lot of grad students to solve all of your problems, and how this is really an exciting field. Thanks, everybody.
Well, thank you, Dr. Bodewits. I think this was an excellent presentation. We probably have several questions, but I'm going to start with my question, since I have the microphone here. What do you expect James Webb Telescope offer for exploring asteroids and comets, especially with regard to the water molecules and that stuff?
Oh, that's a wonderful question. So James Webb was designed by the Astrophysics Division of NASA, and that has pluses and minuses. It is not a telescope designed to observe objects in the solar system. So when things are too close to us, James Webb will not be able to follow them. It's just not quick enough. And you guys know that, right? It's just a question of tracking of telescopes. So, however, it's a big telescope. So it's going to focus on things that are further away from us than ever before. So objects that are in the asteroid belts, objects that are very faintly active, but it's super good at finding anything that has water, carbon dioxide, or carbon monoxide around it. It just will not be good at anything that is close to us. So it will not give you the stuff that Hubble gave us, like comets that are exploding or collisions in the solar system. James Webb is not good at that, but it is good at looking at stuff that is very far away and more of like transition objects. So how do you go from Pluto, a Pluto-like object, to a comet? And that's what James Webb is going to tell us.
Do you have any idea about the differences between the exo comets, or what you call interstellar comets, and the solar comets? Do we know any differences between them?
That's such a rich question. So, at some point, if you haven't, it's going to behave this form, right? ice, but it was still very surprising to see that the one really interstellar comet that we have, that had so much cyanogen, and that it behaved so much like our own comets. It had much more CO. We only had one or two comets that looked like it, still not zero. But if you have one object from another system, you would expect it to be an average object, not an extraordinary object, just based on statistics. So to see that the one object that we got from a different system behaved like the most extraordinary objects that we have, that was just strange. And it suggested that, to me, that maybe this comes from like maybe an M dwarf star that is cooler, it has more CO, it has different circumstances. But you can make this any story you want. We have two objects and only one with chemistry. So it's the low number science makes everything that you conclude from it a speculation.
Okay. Two things, Dr. Bodewits. Please stop sharing so that we can see everybody else. Dina has a question. Dina, you want to ask your question?
Sure. In talking with David Levy, I was surprised to learn that not all comets are solar orbiting. For example, Shoemaker-Levy 9 apparently was actually orbiting Jupiter. Are there many that have elongated orbits around giant planets rather than the sun? Many comets?
So the answer is that our study of comets is very biased.
Okay.
And what I mean with that is that cometary scientists tend to focus on the comet of the year. There's one comet that is going to be very bright and very well positioned for study. But at the same time, there are 400 other comets, and probably 200 of them that are within 20 of magnitudes. And this is going to the study of comets is going to change in the decade going forward with robotic telescopes, with surveys. Suddenly, also the data of all those other 200 comets that normally would have been ignored will be studied, and there are going to be interesting comets that behave differently that we expect from what we expected in that big sample. So if you have 400 objects, there's always going to be one that's weird. and we didn't pay attention to it before because we were focusing on the ones that were bright and that are stealing the show. And I think this is going to be a lot of fun. This is going to be so interesting to see what are those weird objects doing. And yeah, there's one that's there every year. There are a lot of comets that are affected heavily by Jupiter, or that make big jumps in their orbits, or that do other weird stuff. And now suddenly we'll have that data. And this is something that can even be done by small telescopes. There's the TRAPPIST telescopes that you may have known, that those are sub-meter telescopes in Morocco and in Chile that make an enormous impact. There's the Las Cumbres telescopes. That's like 40-centimeter telescopes. Well, and then also people like Borisov, they actually discovered the first interstellar object. So it's not only the professional surveys that are making a big impact. No, this was actually somebody who is not a professional astronomer who managed to discover the most significant interstellar object ever seen before. So yeah, it's a wild population.
Okay, thank you.
John Bickel has a question. John, you want to unmute and question?
Is that on now?
Yes, you are on.
Oh, I've imaged a couple of comets. Most recently, the Leonard back in January, and when I took an image, it was kind of lime green, and I initially thought this is a little bit weird. And I have a friend that's a chemist, and he says, "Oh yeah, I think that's caused by carbon forming out, without any oxygen around it." And I was just curious, what form of carbon is it?
Yeah, I think I can answer that. So that's likely dicarbon, so carbon 2, and this is a fascinating puzzle. So the first people to observe comets in the 1870s, they noticed that the spectrum of comets is very close to that of just ordinary flames. So in ordinary flames, you have the soot that gives you the reflected sunlight in comets, and then superimposed on it, you have small molecules. So it's OH, hydroxyl, and C2, and C3, and CH, and so comets resemble flames. So that's going to be C2, and we don't know where it comes from. It's probably some larger chain of molecules that forms it, a complex molecule, but which one exactly? That's been a puzzle, and
Yeah.
it changes also. Like when a comet gets closer to the sun, there are other sources, other molecules. So these polymers, we don't know what they are, but yeah, so those are the ones that form your green light, dicarbon.
Okay, Jim Wallace is asking, how do meteor showers arise from comets?
Yeah, that's a dynamically quite complicated question. So comets emanate a lot of grains. So you have this gas and it blasts off dust. And this dust is going to have a range of sizes, smaller and larger. And depending on the size, these grains will be pushed away, either exactly away from the sun if they're really small, or they will follow the orbit of the comet when they're larger. And so these grains, they form paths, and they linger for centuries. So, and whenever Earth passes those paths of comets, you get meteor showers. So if they're pretty big and long-lived, for example, with Halley, you get the Ide Aquariids that we just passed. Those are particles that were ejected probably several hundreds of years ago by Comet Halley, and we're passing them right now.
Okay. I have a question about the same interstellar comets. How did we know that it was interstellar?
Yeah, that's very subtle. So if you look at the orbit of a comet and you see that it's not elliptical, so meaning that it doesn't connect back and forth, you could conclude like, okay, it must have come out of the solar system. However, orbits of comets are affected by the interaction with Jupiter. So if you calculate the origin of a comet, you have to make sure that it never interacted with a giant planet before, and it really came from outside of the solar system. And for Borisov and for Oumuamua, they had such a large inclination. So they essentially came from a plane not interacting with Jupiter at all. So there was no way that they could have come out of the Oort clouds. They had an eccentricity that was higher than 1. They had an orbit that pointed them to come from somewhere else.
Okay, thank you. Are there any other questions from the audience? You can raise your hand. Ron, unmute yourself, yeah.
Most meteorites are known to come from the asteroid belt. There are a few exceptions, such as lunar and Martians. There's been some speculation or comment that perhaps some classes of meteorites might come from comets or the remains of comets. Any thoughts on that?
Yeah, that's so fascinating. So what we now know is that the distinction between comets and asteroids is not straightforward, right? There's going to be a gradient. There are objects that have more volatiles. There are objects that have less volatiles. Like some are more dusty, some are less dusty. It's where any science field goes, right? You start with a simple classification, and it turns out to be like, well, this is not just 3 classes, we have a gradient. And that's the same thing with comets. So where it was first said like, well, an asteroid is just a rock, a comet is an icy body, and now it turns there is a gradient between them. Like, well, that's not a big surprise. And so what is exciting is that meteor streams really demonstrate that. There are orbit crossings with objects that are currently not active, so for which you wouldn't expect them to be a comet, but you cross their orbit and it suddenly turns out to be like, well, they leave a lot of dust in their path. And so Chiron is one of them, Phaeton is one of them. They currently don't look like comets, but anytime we cross their orbit, we get these meteor showers, and that suggests that in the past, for some reason, they were active.
Okay. I have Michael, unmute yourself and ask your question.
Yeah, thank you. Great talk. I really learned a lot. I'm going to have to listen again to catch it all. But what I want to know is, did you ever have a "I told you so" moment with your old professor?
No, he always wins. My thesis supervisor was Xander Thielens, who works on organic molecules in comets. And it's kind of funny. Just going back in my research, I had several moments where I was doing my literature research and coming back to his work, and I was like, seriously, I'm going back to my thesis supervisor's papers. He's a wonderful person.
Okay. Tony, unmute yourself and ask your question.
Thank you for the presentation. Do you have any thoughts regarding the apparent acceleration of Oumuamua as it left the system?
Oh, yes, that's a wonderful one. let me start you this way. So I'm a reviewer for Nature, as many scientists are. So, and the editor of Nature was at Maryland when I was there as well. So he called me up and saying like, we have this paper about Oumuamua and it has accelerations. I don't want tomorrow's press release to be Oumuamua was an alien spaceship. How are we going to talk about this and keep this scientific? And so Oumuamua was a very small object, and it was the first of its kind. And we know of comets that they have jets and they change their orbits. This is a common thing, and it's actually a pain in the neck, because if you try to observe a comet with Hubble, you really have to work hard to make sure to know its orbit, the comet's orbit, well enough to make sure that Hubble catches it where he is. You guys are observers. So if you have less than an arc second, less than a tenth of an arc second in your pointing accuracy, you need to, and what happens is that a robot decides on where to point from that. You could see that this can go wrong very easily, right? Hubble has very smart routines, and it searches for any bright object within that tenth of an arc second. And if there's anything else, you will not get your comet. So we've always been working with observers to make sure that we had the orbital solution for any comet that we observe as accurate as possible to make sure this wouldn't happen. So this happens all the time. So it's no surprise that for Oumuamua, there would be a little deviation in its orbit if there was a small amount of activity working over a certain amount of its orbit. And this was a less than a kilometer sized object with really small activity levels, so nobody could see any dust. But yeah, the people working on its orbit then found like this is not where it should be. So henceforth, it must have been active. It's not so. It's an exciting science result and an evidence that there were volatiles sublimating from it. But as a small body scientist, it's not surprising. It just shows you that there were volatiles in this thing. So yeah, we're very skeptical in the more enthusiastic interpretations of what this object could be. I think it's just a small body, just like the ones we have in our solar system.
Okay.
The physics work.
Okay. Thank you.
I would love it to be something more, but
yeah, that would have been more exciting, actually. Any other questions, comments? I see lots of comments thanking you, Dr. Bodewits, for the excellent presentation, but are there any other questions?
I think we're back. I was frozen for a second.
I think we might have exhausted the questions. So thank you very much, Dennis. We really appreciate it. We learned a lot, and we also had fun, and really appreciate your putting together the presentation and delivering it. And thank you very much.
Thank you.
I enjoyed talking to you guys, and I hope you saw my email address. And if you have any follow-up questions, I'd really appreciate you reaching out.
Okay, thank you very much. If you like, you can stay, but we are gonna be stopping the recording and live stream, and then go with the rest of the business. Am I right, Dina?
Yes, I'm going to stop the cloud recording and the live stream right now. Thank you. Thank you so much.
Thank you, Dr. Bowman.
I'm going to enjoy the rest of my evening. I'm an hour ahead.
Thank you.
Thank you for joining us. We appreciate it.